Hi there, welcome to our lesson on volumes of solids. In this lesson, we will be finding volumes of solids through rotation. Recall that when we find volume by thinking about how if we were just finding the 3D space of a 2D figure. In this case, the 3D space is created through a revolution. In this diagram that you see here, you can see that we have created an area, let's call it R, bounded by this line right here, which is x plus 3y equals 6, the y-axis, and the x-axis. As we revolve this area R around the y-axis, this revolution around the y-axis is called the axis of revolution. And as we revolve it around the y-axis, you can see that it basically kind of creates this, this cone that you see on the right-hand side. Okay? Now, all that can be a little complicated, so let's actually dissect it into smaller parts, just as we have seen calculus do for us in previous lessons. Okay? So on the picture below, you can see that the area R is formed and can be thought of as a series of rectangles, right? We can just build a bunch of rectangles just like this. Now, we've seen that in previous lessons, that if we wanted to find the area between two curves, you can really just think about it as the area of the summation of rectangles. Now, if we were to actually take one of those rectangles, let me just erase all this. If we were to actually just take one of those rectangles, we can see that the area of the rectangle can be found by multiplying its length and width. Its length, given from, and here from the y-axis all the way to this line, and its width given by this part right there. Now, what is this length? Well, we can think of it as going from the axis itself, or in this case x equals 0, to the equation of x plus 3y equals 6. More on that later on. Let's call it L for now, though. Let's call this length L, okay, or length x, whatever you want to call that. Now you can see that its width, based on how the number of rectangles might change, the width can also change. And that width, since it's going along the y-axis, we're going to call that dy. Okay? So our width is dy, and as the rectangle spins around, you can see that it's going to just take that line and revolve it around the axis of revolution. And as it spins around, you can see that this thin cylinder is formed. You can see that the thin cylinder is right there. Okay, so that thin cylinder is formed. So how can we find the volume of just one of these cylinders? Well, what we can do is take the area of its base, and the area of its base, you know, it's a circle, so therefore you know the area of its base is pi r squared, and then just multiply that by its height. And so since its height is represented by this dy, we can just multiply that by its height, or let's call that dy. Okay? Or in this case, what we can say is pi x squared, and then the height is dy. That's how we're getting this formula right there. Now, the x, don't really consider that as the actual x value. Just know that the x is really represented by its radius. Maybe x is a bad way to write it. Let's just say pi r squared instead. Pi r squared dy. Okay? Now, remember that this is only the volume of one slice. And we know that if we want to find the volume of the entire cone, then what we need to do is add up all of our slices together from bottom all the way to the top. Okay, so I'll try to show you the demonstration in my next slide here, or my next app here. Okay, there we go. Okay, so you can see that what I've done here is I've basically tried to recreate the same example that you saw on the, let's call it, previous page. What I've done is I've created the equation that x plus 3y equals 6. I just put that in slope-intercept form right there. Okay, and then I also listed the parameters where I'm going to set the number of rectangles, go from the a value of 0 all the way to the x-intercept, which is going to be the b value of 6 that you can see right here, b equals 6. Okay, so we just want the number of rectangles to occur within that space there. Okay. All right, now what we also know is that if we increase the number of rectangles, then you're basically going to minimize the error that can occur, because you can see here we definitely have some space that is unaccounted for when we're trying to find the area under the curve. But if I increase the number of rectangles, you can see that the error is basically minimized as we create more and more rectangles. Okay, so that was our lesson on limits from way back then. So we're just kind of taking that idea and bringing it into this here, and then we're going to create the volume of our solid. And the way we do that is we can rotate all of those rectangles around. In this case, we're going to revolve it around the x-axis. You can see that all those rectangles get moved. It gets rotated around the x-axis like this. Okay, so it's going to go all the way around. And you can see that as it goes all the way around, it's basically going to create a sweeping image of a circle. And that sweeping image, you can just think as it goes along, it's going to create more and more volume. And then cylinders are going to be formed for each of those rectangles. Let's actually show those cylinders. Okay, so I'm just going to go up here. And then I'll show you that those cylinders are created as you get that sweeping image. Oops, make this go away. Go away. Go away. Nope. Hide. Go away. Ah, there we go. Okay, so we see those cylinders are formed. Oops, this is a bad view. There we go. Okay, and as we rotate this, you can see you create that basically almost what looks like a funnel, right? We're going to make this a little bit darker, less translucent, and so we form a solid out of this. You can just see that each of those cylinders are basically solid cylinders. You can think of them almost like coins, and each of those coins are stacked one upon each other, and you form this solid shape. And you can see it almost looks like a funnel, like this, right? You can make it like that, make it a funnel. And again, as you increase the number of rectangles, you can see that the shape actually starts to form where it actually creates that curve, and you're going to have less and less error occur between them until you actually get almost like a true funnel, right? It's not going to have those jagged edges anymore. Okay, so you'll see that's basically our volume like that. Okay, and just think, with calculus, if we just add up the infinite number of rectangles, then you're going to have no error at all, and it'll just be nice and smooth. Okay. All right. Well, let's actually find the volume of our example here. Okay, so let's go down below, and let's find the volume. Do example 1. Okay. So, as stated before, if we want to find the volume of just one slice, what we want to do is revolve around the y-axis. And in revolving around the y-axis, we know that its width is going to be represented by dy. Okay, so the width is dy, which means we want to make sure everything is in terms of y. So make sure that everything is in terms of y. Now, we know that the area of its circular base, this circle right here, is pi r squared. But what is its radius, though? We got to find its actual radius. Well, we know that the radius of the circle just goes from the axis of revolution all the way to its line itself, which is x plus 3y equals 6. Now, if we want to find that length, remember that we can find length by doing the rightmost function minus the left function. Now, the right function is x plus 3y equals 6. Keep in mind, we want everything in terms of y. So let's write this in terms of y then, which means what we want is that x is equal to 6 minus 3y then. So the radius is going to be made up of 6 minus 3y, and we want to make sure we want to find the distance all the way to this value here, which in this case is x equals 0. So we're subtracting 0. Well, in this case, the radius is really just 6 minus 3y. Okay, so the radius of our image, this is getting a little confusing here, let me erase all this. The radius of our image is going to be 6 minus 3y. The area, therefore, is going to be represented by pi times r squared. Our r being 6 minus 3y squared. This is like our pi times r squared, the area of the circle. And then we got to multiply that by its little bit of thickness, which we can call dy. And this represents the volume of just one slice. Now, think about this. We want the accumulation of all the slices. So what do we have to do? We have to add up all of our slices. Well, where do those coins start from? Where do those cylinders start from? We have the bottommost cylinder right here, which we know we can see that it's going to start at a y value of 0. And you just keep adding cylinder upon cylinder upon cylinder upon cylinder. Well, when do the cylinders stop? When you actually reach this part right here at the y-intercept of this line. What's that y-intercept of x equals 6 minus 3y? That's going to be a value of 2. So we're going to integrate from 0 to 2 of each of these cylinders. Pi times 6 minus 3y quantity squared dy. Okay. Now we know that since pi is just a value, a constant, we can just move that out, right? So I'm just going to move it out. And that'll just go to the left of our integral. And then from here, it's just basic arithmetic, right? We're gonna distribute this. So we're gonna get pi times the integral from 0 to 2, and then 6 minus 3y quantity squared will give us 36 minus 36y plus 9y squared. And all this is, remember, is with respect to y. Okay. From here, you can actually integrate. So we'll pi times, and then we'll get 36y minus y squared, 18y squared plus 3y cubed. And all this is going from 0 to 2. Okay? And then we can plug in our values. So we'll get pi, and then times 36 times 2, so 72, minus 18 times 4, 72 plus 24, and then we know that's going to be minus, basically everything's going to be 0 there, so that's it. So it looks like we're going to get a volume of 24 pi, and that'll be it. That's our volume. Okay. Let's take a look at our next example. Next page. Oops. Let's move this up. Move this up. Okay. So depending on how we rotate about the line, you may actually get a horizontal axis of revolution or vertical axis of revolution. The main thing that you want to keep in mind is that if you are rotating about the x-axis, you're going to have that basic change in x for the width. So you're going to have this all in terms of x. So just keep that in mind, that if you're rotating about the x-axis, the horizontal axis of revolution, then your width is changing by x. So you want to have a dx in your equation, which means that when you find volume of a disk, you're going to take the area of the disk, the pi r squared, and multiply that by the width. Well, the width in this case is going to be dx. Okay, so the width is dx there, and then this is your area of the disk. Okay. Now when it comes to the vertical axis of revolution, keep in mind that your vertical axis of revolution is going to revolve like this, which means that each of your areas is going to have a circle like this, but you're going to have a width of dy. If you're revolving almost like around a y-axis, you need it with respect to y. So dy is going to represent your width, and then your area, the pi r squared, needs to always be in terms of y. So you'll notice this in terms of y here. When you're doing a horizontal axis of revolution, you need to make sure that everything is in terms of x. Okay? All right. Let's go on to our next example. Y equals negative x plus 1. We're going to find the volume of this solid by revolving about the x-axis. So we're going to revolve about the x-axis. So it's going to look like this. Now I also need to draw my line in, so let's go ahead and draw that. Negative x plus 1 has a y-intercept at 1, and because it has a slope of 1, we're going to go down 1 and over 1, and it will have an x-intercept of 1 as well. So therefore my line will look like this, okay, like that. And so therefore, since we are going to contain this region, this R, by the y-axis and the x-axis, we see that you do form this triangle here. Okay. Now, because we're revolving about the x-axis, think about what kind of rectangles you're going to have. If you're revolving around the x-axis, do you want horizontal rectangles or do you want vertical rectangles? Hopefully, in answering that, you are saying you want those vertical rectangles. You want those vertical rectangles because what you want is to form those disks like this. So you want to create a cylinder that would look like this. Okay, so what we're going to do is think about what our rectangles are made up of, right here. Since it's revolving around the x-axis, we see that we do have a slight width of dx, meaning we want everything in terms of x. In terms of x. Okay, so think about the volume of just one solid, one disk. We know that one disk is going to be made up of a circle, which is pi r squared, and we want to multiply that by its height. Its height is right here, and that's going to be represented by dx. Well, what's its radius? We got to find out what its length is here. Well, we're going from the line itself, which is negative x plus 1, and we're going all the way down to 0. So its length is going to be negative x plus 1 minus 0, or in this case, it's really just negative x plus 1. That is what its radius is. The radius is equal to negative x plus 1. So we can go ahead and plug that into our equation. We have pi times negative x plus 1 quantity squared, that's pi r squared, times h, which is dx. We're going to need to add up all of our cylinders. And those cylinders, if you notice, it's actually going this time from left all the way to the right. So you'll create a sideways cone, basically. Okay, so where are we starting from? From the very left, it looks like we have an x value of 0. And we're going all the way to an x value of, stops right here, at 1. We're going to go from 0 to 1, basically. Okay, so just like we did in our previous example, let's just go ahead and do the basic math to this. So we have, I'll move the pi out, so 0 to 1, and we need to distribute that. So we will get x squared minus 2x plus 1, and then don't forget this is with respect to x, so dx. Alright, we can integrate this, so we're going to get pi, and then multiply that by 1/3 x cubed minus x squared over 2, so just x squared plus x, and this is going to go from 0 to 1. Alright, plugging in our values, we're going to get pi times 1/3 minus 1 plus 1, and then because they're 0 again, we're going to minus 0, 0, 0, so 0 doesn't really need to be included. Alright, so from there, you see negative 1 and 1 cancel, and what we're left with then is pi over 3. That is going to be our volume of this example here. Okay? Alright, let's go on to our next page. Why do these always go to the bottom? Alright, let's go to the top. Alright, here's our next example. We have y equals the square root of x. Think about what that looks like. That's a square root function. No transformations, so just square root of x like that. And we want to bound it by x equals 0. So our bound is x equals 0. Our other bound is x equals 4. So we'll bound it right here at 4. And oops, wow, that's awful. And by the way, since we are bounding at 4, we might as well figure out what this point is. That's probably going to be useful, right? When we're doing square root of 4, that looks like it's going to be the order pair 4, 2. Okay. Alright, so from here it says we're going to revolve about the x-axis. Think about what this looks like. If we revolve about the x-axis, we're going to get this shape. If you notice that each of these rectangles are going to form like this. You have each of these rectangles like this. And when you revolve it, you're basically going to get a shape that would look like this. Kind of like a bowl, right? It's almost like a parabolic bowl. Alright, so let's go ahead and find the volume of this. We know that we're going to take each of these rectangles. So I already drew a rectangle here. We know that based on this rectangle, its width is made up of a dx, and its height, well, we'll find that later. But for now, we know that because we're working with dx, we know the volume of one of those cylinders is pi r squared times h. Its h being that dx there. Okay, and now we just got to plug in the r value. The r, the radius, just goes from top to bottom. What's that radius? The top part, since we want in terms of x, would just be square root of x minus the bottom, and that bottom is, oh, well, it's just 0. So the radius, therefore, is just a length of square root of x. So we can just plug in square root of x right into the r value, pi square root of x squared dx, and this is representing the volume of one slice. Keep in mind, we want to add up all of our slices together from, let's see, we're going from the smallest slice here, and it gets larger and larger, so a smallest slice of, going from 0 all the way to the slice of, all the way over here, to 4. Okay, so we're going to find our volume is equal to that equation there. Now, square root of x squared, we know that's just going to be x, so we have volume is equal to pi integral from 0 to 4 of x dx. We know that the integral of x is 1/2 x squared, and this is going from 0 to 4. Okay, plug in our 4. 4/16 over 2 is 8. We get 8 pi minus 0 pi, or we'll just get a volume of 8 pi. All right. Next example. Y equals x squared. All right, so we're just going to do the inverse function then. So y equals x squared. But this time we have both the left and right side, right? In the previous case, we just had square root of x, not negative square root of x. But here we have x squared, so we're going to make sure we include both parts. Okay, so we're going to revolve about the y-axis, meaning let's always draw this. Let's always draw our axis of revolution and show the revolution. Okay, and we're going to revolve from 0 to 4. So we're going to go from 0 to 4. We're going to stop at 4. Ooh, that's horrible. Let's stop at 0 to 4. There we go, like that. Okay, so we're just going to cut it off there, and we just want to find the volume of this space there. Okay, now, because we are revolving about the y-axis, keep in mind that we are actually creating those horizontal rectangles now, which means you see that we're going to have a width of dy, or rather a height of dy. We know that our volume of each slice is going to be pi r squared, that's the area of a circle. Turn it into a cylinder by multiplying by its height. Its height is, you got it, dy, so we want everything in terms of y. So we want our equation actually in terms of y as well, okay? All right, so, oh, well, that's not right. We have y equals x squared, meaning x is equal to plus minus the square root of y, okay? So, in plugging that into our radius then, we're going to get pi times the radius, which is the square root of y squared. But because it's being squared, we know the square root and square will cancel out. So what we're left with then is just pi times y dy. And we want to integrate this from, let's see, we got each of these rectangles from 0 all the way up to 4. So 0 to 4 of pi y dy. We did that already, up here, right? That was pi integral from 0 to 4 of x dx. Does it matter whether it's x or y? No, you're still going to be doing the same thing. You're going to integrate it, but just rather than x, you have y. So we can see that this answer is just going to be 8 pi, not 8y. What am I doing? 8 pi. Okay, there we go. So same area, or same volume rather. Let's go on to our last example, example 5. Y equals e to the x. Do you remember what that looks like? It's our exponential growth function. It has a y-intercept at 1, and it's going to come up like that. Oh, let me draw that a little bit better. E to the x is going to come up like that. Okay, and it's going to revolve about the x-axis, so revolve around the x-axis from 0 to 2. So I guess it's kind of important to also figure out where this part is. We know that it's going to stop at an x value of 2, and if we plug in 2, we're going to get e squared, basically. Okay. All right, so if we're revolving around the x-axis, what do we have? Do we have horizontal rectangles or vertical rectangles? Well, if you're revolving around the x-axis, you want that to be vertical rectangles, so you have a dx there. You want this in terms of x. Okay, so we'll have vertical rectangles like that. So let's think about our equation again. Pi times r squared times h. The h value is the dx itself, and the radius is going to be the length of our rectangle there. How high does that go up to? Well, it's always going up to this ex, right? The radius is going to be made up of top, which is e to the x, minus bottom. In this case, it's just 0, so the radius is just going to be e to the x. Okay, so let's plug that in. We're going to get pi times e to the x squared, or that's the same thing as pi times e to the 2x dx. And we need to integrate this from, let's think, we want the leftmost rectangle starting here at a value of 0, and we're going to have all those rectangles go until, that's right, 2. Okay, so our volume is equal to integral 0 to 2 of pi e to the 2x dx. All right, well, let's integrate. Let's take out the, with e to the 2x, that's going to give us volume is equal to pi, and then what do we get there? E to the 4 minus e to the 0 over 2. Okay, and from there, we're going to get a volume of pi over 2 e to the 4 minus 1. Then e to the 0 is just 1. And, well, let's not use a calculator. Let's just leave our answer just like that. Okay. All right, so that'll be our lesson for today. That was just on volumes by rotation. And we haven't really done anything too complicated just yet. We'll see that in our next lesson. We'll save that for next week. Okay. All right, well, go ahead and do your homework. You've got all those worksheets. Check on Google Drive if you need to print anything out. And I will see you in the next couple days.